welcome to the Camo Monster. In this video, we are going to learn about the design and construction of equipment setup for the extraction of oil from Jatropha seeds. You can use the same method that will be discussed here for the extraction of oil from soybean, from sunflower seeds and canola, many different type of seeds that have oil. First of all, for the solvent extraction, you need a solvent extractor like here it is used, and a methanol evaporator that is used as a regenerator to recover the solvent from the mixture of raffinate that contains the solid and the solvent and the oil. Now, first of all, we need the material and energy balance as usual for we have obtained from the other designs that have been discussed, like the mass of oil required here is equal to the 21,742 kilogram per hour, and the oil content of the seeds are 40%. This is based on the assumption, and a valid assumption is followed by a strong literature references, and in most of the references you will conclude that the oil that a seed can contain differs based on the location, based on the zones, based on the season, and based on the way they are cultured on the sand. And sometimes the soil can also play its role in the growth of the seed inside the flower or the plant. So here the 40% oil content of the seed weight percent is considered, and we always have certain efficiency of your equipment. Like for achieving the efficiency of separation, here we consider it to be 78.66%. The mass of seeds that are required or that are entering into the equipment for the extraction are 69,101.77 kilogram per hour. Now, first of all, we have to consider certain assumption, like 100% of the hexane is removed by evaporation due to the large difference in boiling points. And it is actually okay because N-hexane have certain boiling points under 100 degrees centigrade, while the oils have large boiling points above 100, above 200, or sometimes above 300. So oil content of seed here, amount of oil successfully extracted. Jatropha contains 14% free fatty acid. Okay, it can be said because the oil contains two chains of the fatty acid or non-fatty acid. So here the hexane to oil ratio taken from the experiment of the equilibrium data, like discussed in the absorption column video, that always an equilibrium amount of solvent is required to absorb certain amount of solute. That shows the maximum capacity of it to handle it. Like in this case, we have selected 1.5 ratio of oil to ensure that the Jatropha oil of required quantity is fully dissolved. Now the conditions, for example, we have the temperature 90 degrees centigrade and the pressure is 1 bar. So the separation will be achieved based on the boiling point differences that will be in the evaporator. But during the extraction of oil from the seed using a solvent in the solvent extractor, you need certain kind of mass transfer relations in addition to that. Certain kind of mass transfer, because there is a mass transfer involved between two liquid phases, and there is also a solid surfaces involved which contain the solid. So the oil inside the seed diffuses through the pores or the surface of the seed, and it comes out to be in the mixture, and then the solvent N-hexane or ethanol you can use, it will dissolve that oil. Most of the times the oils are crushed down to extract that oil, but it is expensive technique and you can lose a lot of oil in mechanical presses. Like But in the solvent extraction, with a reasonable amount of temperature, the oil have the capacity to destroy the outer embryo, of the seed. So the oil entrapped inside the membrane of that seed embryo is extracted out, because there is an embryo coating outside, so you will not always say it is porous. Actually, it is non-porous most of the cases, because coating is tough. The embryo coating is always tough of the seed, like eggshell coating. But most of the time, it can break easily if you press it. It can handle only a certain pressure. So the solvent boiling or vapor pressure will provide enough pressure in a clean, neat way, because whatever comes out from that seed due to vapor pressure of the solvent, it will be absorbed inside the solvent. So there is no problem about the loss of oil based on the solvent extraction. So like here, you have to first calculate the properties of the oil. Like here, the diesel is compared with the Jatropha oil. The density, kinematic, viscosity, cetane number, most of them will not be used here, expect the density or sometimes viscosity, but it is discussed here for the references. Now, most commonly, if a person will face the design of a seed extractor using the solvent type technique, he will ignore in the most cases the mass transfer rates, the equilibrium capacity or mass transfer stages or mass transfer contacting time in the extractor, and he will directly move toward this type of design I am showing first, and then I will show what is the correction that is needed in this design. So the desired capacity, like I have told before, is 21,742.18 kilogram oil per hour. From the energy balance, simply for each component enthalpy, like you can, from this mixture you can use an alternative of average mixture specific heat, so you can use the enthalpy. From that you can calculate the total heat that is exchanged in the extractor. Like you have heated the mixture up to the 90 degrees centigrade, so the heat is exchanged between the 90 degree and the feed temperature at which the solids and the hexane enter at the equipment or extractor. Like here, the CP of Jatropha seeds is assumed to be 750 joule per kilogram Kelvin with 10% moisture. The moisture is always remains on the surface of the seed. Sometimes CP of hexane is taken as 2.35 kilojoule per kilogram Kelvin, and the CP of Jatropha oil in the literature is found to be 3.5 kilogram per kilojoule Kelvin. Like we have certain kind of extractor operating conditions also, like here I am again saying T in 25 degrees centigrade and T of 50 degrees centigrade, assuming that no temperature gradients or dead zone exists inside the extractor. So using this equation we can find out that the heat released during the whole extraction process is equal to 8,74386.4 kilojoule per hour. The weight of exhausted seed cake can be very simply calculated from the material balance, like total seed minus the total oil extracted. It will be exhausted seed cake amount. But during the heat transfer, a heat transfer coefficient is involved with its area that is providing the heat. Like for example, if we are using the coil of copper with a boiling water stream inside, its coefficient, like assumed, is to be near from the literature references 670 watt per meter square. As I have told last in the design of a shell and tube type heat exchanger, that during the phase change there is no temperature change involved. So most commonly these reference based heat transfer coefficients are used. Based on this, the design area, if you are telling it to be heat transfer area of coil, it comes out to be Q over U multiply A. The temperature difference is in this case 50 minus 25. So like area comes out based on the design area of heating coil is 14.6 meter square. But in other case, you can also say the there is some kind of mixture inside the vessel, not only the coil. So the design area of heating coil will be a factor, but not the complete design. So you also have to understand what is the volume that is flowing inside the vessel. So you can base our design on one more important justification, like we can say the volume of the mixture inside the vessel, like here, but it is the same. For example, you are designing the evaporator. The design technique based on heat transfer coil is actually okay for the area of the evaporator, but not for the extractor, because there is some volume. Like volume is calculated using the mass over density of seeds, or based on the composition density of mixture. It can contain different composition in different fractions. So the total area added into the extractor column will be equal to the volume of solvent per extraction plus volume of Jatropha seeds. Like it comes out to be 37.35 meter cube. Now the volume of extractor is given by pi di square h over v. V is noun, dt is 2.67, that is assumed above from the heat transfer area of coil. We are assuming the heat transfer, the coil is actually covering the whole diameter down the coil, so the coil area will be equal. You can actually take the slightly larger diameter, because it is not good that your coil in which the heat transfer is taking place is touching the walls, or it is packed strongly inside the column. So getting a slight larger diameter based on your heat transfer diameter calculation above, you can calculate the height, that in this case comes out to be 6.6 meter. The same can be said for the design calculation of evaporator. That is actually simple bit. Like I have only considered it a plate type. So in the case of plate type, there are no tubes. There are no specific internals, no baffles, no tie rods, no spacers, nothing else. Like conventional shell and tube type or double pipe type. Double pipe is actually simple, but a plate type is actually too much simple. So evaporator based on a simple plate type will only be followed by the calculation that is defined above. Q is equal to UA delta T. So from that you can calculate the area of plate that is needed to evaporate the oil. But I think you should get a certain kind of suspect or doubt about the design. There is something missing actually. There is no parameter, or there is no relation that is defining the mass transfer inside the column, because even the whole volume is enough to flow inside the vessel. Like we have a 14 meter cube volume mixture, for example, and we have 14 meter cube vessel, so my design is completed because the vessel volume is enough to contain the mixture volume, or the heat transfer is enough to maintain the temperature that is needed for the extraction. Not enough, because the design is always based on the mass transfer calculation. Because even if the volume is completely filled inside the vessel, you can't say your certain amount of efficiency or separation, like if you want to separate 99% of the oil, is achieved, because you do not know that how the mass transfer is actually taking place, how the equilibrium is maintained, and how actually the solute is being transferred from that seed out from the seed to the outside surface and then to the solvent. So you have to add certain kind of additional mass transfer calculations inside it based on the mass transfer between the oil and the solvent. So I am showing this calculation from the International Journal of Chemical Engineering, Hindawi. The oil extraction is based on the Jatropha oil seeds like defined here. And first of all, for the extraction, you have this relation: the concentration of oil extracted at any time for each experiment based on the equilibrium concentration is calculated using this relation. Yt is equal to Cl, volume of solution, divided by m naught, the solvent volume utilizes Vsol, and m naught is the total oil mass in the sample, like here total oil mass in the sample m naught multiply 100. So the oil mass in each sample was calculated to be equal to this, where MAM is the dry sample of dry mass of the sample with moisture content. So this is only the concentration relation or the mass transfer relation, but there is some kind of rate relation, like you have read in the mass transfer and heat transfer by BK Datta, or like you can say the flux equations of Fick's law, you can say Fick's law first and second order differentials, or using the transport phenomena relations based on the mass transfer contact, chapter 3 or 4 Rionberg. So like here we also have a kinetic model that is defining the rate of the mass transfer, because if a vessel needs 10 minutes to extract the oil, the volume based on the efficiency will differ from the vessel or equipment in which there will be 5 minutes required, because more the time required, the more will be the more must be or should be the capacity of the column to handle the mixture, because you have to maintain a flow rate. It is not the batch process. It is not actually the batch process, again saying to in which that is the system is independent of time, because a function in a continuous system is followed by other chain system. Like if a reactor is disturbed, or it actually takes more time, so the separator attached with it will be disturbed. The heat exchanger attached with it will also be disturbed. So you have to take care about the kinetic models or the rate based function, time based function, in which the time is a dimension, not the xyz. Always the xyz is defined above the relations based on the mass transfer concentrations, like here. Okay, so the here steady state function, as you see in the reaction kinetics, is shown, but it is actually, the k is not the reaction constant. The k is a mass transfer coefficient here per minute, while oil concentrations are given in the liquid phase at t time minute gram per liter. Okay, from solving this equation, if it is first order, you can simply get this relation or this relation. From this expression, if you know the yt concentration at the end, the concentration of initial liquid phase at equilibrium, this is equilibrium, not the concentration that is achieved based on each stage. It is equilibrium composition that is achieved finally. So that is based on the experimental techniques, and you can most of the times you take it from the literature, but based on the solvent extractor or the systems in which the solid slurries mixtures are used, most of the times you do not get enough their data, so you can iterate your system and get a reasonable answer based on it. So like time, if the time is calculated here, so you can calculate the overall volume required based on that time. Like I have a flow of the oil that is required 29171 kilogram per hour. The time has been multiplied, and you can calculate only the mass, that mass based on the equilibrium contact, and from that mass you can convert to volume using the density. So a volume will be attained that will be based on the mass transfer and equilibrium contact time. So it will represent a better answer, but not that much, because a performance criteria or equation is not defined. Like in the reaction kinetics, you have V over Fa naught is equal to X over minus Ra. So a design equation is actually defined to bound your limits to some certain kind of optimized values, but it is not actually too much optimized function, because a performance criteria is not involved, but it is reasonable justification to get a contact time and to get a volume based on it. So this is actually overall the theme for the design of a solvent extractor or evaporator system for the extraction of any kind of oil from any kind of seed using any kind of solvent. So stay happy, stay blessed, and stay with us. Thank you.